them to all your friends? No? Okay, well, if you get some more at other schools, then maybe you can send it to them. Oh, I was wondering who that was. I was like, that's really random. Thank you.
And I turn post notifications on.
Wow. What a fan. What a fan. Okay. All right, so we have an idea of the notation that we use with functions. We also have kind of an idea of how we can evaluate in those functions. We also think of functions kind of like a machine. So that's kind of what we talked about in our second part of our lesson yesterday. So a function is like a machine. It takes in an input, it does a set of operations, and it gives an output. So we talked about like some machines that we have in everyday life that do a similar thing. When we talk about functions as a part of like a math machine, I guess you can call it, the operations that are performed are like multiplications, divisions, addition, subtractions, square root, squaring, things like that. Okay? If you still have your phone out at this point, now would be the time to set that away in your backpack. Okay, so there's still a little bit more that we need to kind of build on our idea of a function. Okay? So we've got something called a relation, and we've got something called a function. A relation is basically anything that you might be presented with in your math courses. So it can be any set of data. Okay, I'm going to go back to that first slide in a second, but I want to do this guy first. Any set of data, and some examples that you might see would be a table of values, a set of points, a graph, or an equation. So those are all examples of different ways that we can represent sets of data. Okay, so our relation, I want to think about that as like the umbrella for like all of this stuff that we're doing, right? Like if we are approached with a table of values or a graph or whatever, we want to think about, okay, this thing is a relation. It's a set of data. Now functions, these are a little bit more special. So functions are a relation. They're a specific set of data that we get. So that's the first point. A function is a relation. But there's kind of like a special criteria that has to be met for something to be considered a function. And that criteria is, for every x value, I want to have a unique y value. Okay? So we're going to say where each x value has a unique y value. In plain English, basically what you're looking for is in your set of points or on your graph, if you have two x's that are the same, we don't want them matching up with two different y coordinates. Okay? That's kind of in plain English what we're looking for. So duplicate x values do not match up with more than one y value. Okay, so that's kind of like plain English. That's what we're looking for. So if you see an x value repeated, we want to look at their y values. If they have two different y values, not a function. It's still a relation, but it's not a function. Okay, so function is kind of like under the umbrella of relations, but we need that criteria there to be present to decide if we have a function or not. Okay, so a couple things that we can do are mapping diagrams. These can help us decide if we have just a relation or a function. So I'm going to go back to the first slide there. Is everyone good with this? Wait? Okay. You sure? Okay. Anyone else? Need a second? We're good? Okay. So mapping diagram. When I have a mapping diagram, this is just kind of a visual way that I can tell if something is a function or a relation. So what I'm going to do is I'm going to put my x's in this, and I'm going to put my y's in this. And usually what we would do, it's not like super important that we do this, but usually what we would do is arrange them lowest to highest. So I'm just going to take each of these x coordinates here, and I'm going to write them in a line in my first little oval. And then I'll take my y values, and I'm going to arrange them in my second oval, lowest to highest, no duplicates, okay? No duplicates is an important part of this. So if a point has an x or a y value that is duplicated, you only write it once. Okay, so didn't want that to erase my whole thing. No duplicates. Okay. So we only write the value once if it's duplicated in a point, okay? So right, so only write it once. Why? Why do I need to write it twice? I have the number right there.
But I thought, what? Yeah, it's not a function.
Okay, hold on.
No, but one's x, one's y.
Yeah. So don't duplicate it in its own, like if I have duplicate y values, see how I have a 2 here and a 2 here? I'm not going to write it twice in that second oval, right? But if I have a 2 as an x value and a 2 as a y value, I definitely want to put both of those. Okay? So here's the point. You're getting ahead of me right now, Karen. She's too excited about the mapping diagram. Okay, so we're going to draw lines to the things that match. Okay? So 1 is paired with 2, so I'm going to draw a line from the x coordinate to its matching y coordinate. And we're just going to create how those x's map with which y's. So 2 maps to 4, 5 maps to -1, and 6 maps to 2. Okay, again, this is just a visual way that we can tell if something is a relation or a function. So here's what I'm going to look for to decide on whether this is a function or not. I want each x in the first oval here to only have one line going from it. Do I have that? Yes, so this is a function, okay? Okay, so each x, so the x's in the first oval, should only have one line going from it if it's a function. Yep. All right, so that's what we're looking for. I want just one line going from each of my x's. Okay, let's try it for the second one. So I'm going to arrange my x's, usually lowest to highest, no duplicates. So -2, 4, and 9 will go in the first one. I'm using the first set of coordinates here. And then in the second one, 3, 4, 5, and 10. Okay, now we're going to do our mapping. So write the lines that match from each x to the y that they go with. So 2 goes with 5, 4 goes with 4, -2 goes with 3, and 9 goes with 10. Okay, so now if we look at the lines that are going from each of the x coordinates, we only want one line to be going from each of the x coordinates. Do we have that? No. Okay, so we can see here that this -2 is mapped to 3 and also 5. That makes this, it's still a relation, right? It's a set of data, but it's not a function. Okay? Okay, so it's just a set of data, but it can't be further classified into a function. Okay, so do we need a mapping diagram? Maybe not necessarily. Mapping diagrams can also help us with something that we're going to learn a little bit later today. But I think we could probably just look at the set of points and see if we have x values being repeated matching up with 2 different y's, right? So I don't think we need to do this mapping diagram every single time here. So if we just look at this set of points down here, I'm just looking for unique x coordinates. That's what I'm looking for. So do we have any x coordinates that are being duplicated here?
No.
So this is a function. We're good. Okay? Y values are fine if they're duplicated. It's just x's that we're looking at here. So this guy's a function. Okay, how about number 2? Do we have any duplicate x coordinates?
Yeah.
We do, and are they matching up with different y coordinates? Yes, this one matches up with 2, and this one matches up with 5. So this is not a function. It is a relation. It's a set of data, but it's not a function.
What if it was like -1 and 5 for both of them?
So that is actually still a function, because it's matching up with the same y coordinate. I don't think we would usually, if we have a set of points, we don't usually duplicate the point. But yes, that's a good question. Okay, so if we had -1, 5, and -1, 5, that is still a function. It's not matching up with different y values. Okay, so that's all well and good when we have a set of points. What if I have a graph that I'm looking at? Okay, so then it's a little bit different, right? So we do something called the vertical line test if we are looking at a graph. So any imaginary vertical line that you can draw through your function that is on a graph, or your relation, I should say, should only ever go through your graph at one point. So if I draw a bunch of imaginary vertical lines through my function, I'm looking for it to only ever cross once. The second I can draw a vertical line and it crosses through more than one point at a time, it's just a relation and it's not a function. Okay? So any vertical line you could draw through your relation should only cross through one point if it is a function. Okay, if it crosses through more than one point, then it's a relation, but it's not a function. Okay, so I'm going to draw you 2 examples here, and we're going to take a look at what we see with those examples. So you guys can just draw something similar to what I draw. Okay, so I'll try something like this. Okay, that's going to be my first one, and then that's going to be my second one. Okay, so it's not necessary for us to actually draw the lines through unless you feel like you need to. I'm going to show you right now just as the initial example. So imagine we're drawing vertical lines through here. I'm going to actually draw them, okay? Do you notice that any vertical line that I could possibly draw through this function is only crossing at one point every single time? Okay, do you see any of these vertical lines crossing through more than one point?
No.
Okay, so this is a function. Okay. All right. So that guy's a function using the vertical line test. Now if I look over at this second guy and I start drawing vertical lines, I've got vertical lines crossing at one point only. But what happens when I get to this little loop right here? It crosses through like 3 times here. So I've got a point crossing over here, a point crossing here, and then another point crossing there. So as soon as I get a line that goes through multiple points like that, I know that this is a relation, but it's not a function. Okay? Any questions on that one?
It's a relation, right?
Yes, it is a relation. Any set of data is a relation, right? It can be a graph, equation, whatever. Okay, so this is a relation.
What's the difference between a relation and a function?
Ooh, can somebody answer that question for us? What's the difference between a relation and a function? Great test question.
A relation is like any set of data
Any set of data is a relation, yeah.
Function is where the x value has unique y value.
Okay, so a relation, that's kind of like the overarching umbrella, right? The relation is any set of data. So if I throw up a graph on there, that's a relation, right? Guaranteed. It's a mathematical set of data. The function is a special relation where the x's, duplicate x values do not match up with different y values, right? So each input has a unique y value to it. Zion. I think I would be fine with either. Okay, good? All right, so we're going to talk about domain and range now. So a couple terms that we need kind of set up for ourselves are real numbers. If we're going to do domain and range, we should know what domain and range are. That would be helpful. So real numbers. So in math, we actually have certain sets of numbers and we have symbols for them. So the set of real numbers, the symbol for them is kind of like an R with like a double bar on the side. So that's the symbol for the set of real numbers. Real numbers. Okay, Carlo, can you tell me a number?
Any number?
Any number.
Okay, 4.
Okay, 4 is from the set of real numbers. Now let's be a little bit more creative with our numbers here, people. Can somebody tell me something?
36,000.
Okay, 136,002. Oh, 436,000. Okay, and 2. Okay, that's good. What about negatives? Negatives, yes, are part of the set of real numbers. 0. 0 is part of the set of real numbers. How about fractions and decimals? Yes, they're part of the set of real numbers. Okay, so some examples of real numbers are positive and negative. They can be decimals. Running out of room. They can be fractions. 0 is part of the set of real numbers. They can be square roots, the square root of a positive number, stuff like that. So decimals, fractions, positive, negative. Essentially, it could be pretty much anything that you can think of from negative infinity all the way to, yes. Okay, so mostly anything you can think of from negative infinity. Yes, that's a very good question. What isn't a real number? That's the better question. So this is the symbol for infinity, right? It's like a sideways 8 from negative infinity to positive infinity. Okay, so not a real number. Yeah, so like a fake number. So not a real number. A really good example of this, something that you're familiar with, is the square root of a negative, right? So the square root of negative 8. Okay, we know we can't square root a negative. So square roots of negatives, those are not real numbers. We also know that we can't divide by 0, so something like 2 over 0, that's not a real number. It's undefined, right? So some of those things are not real numbers. Yeah, your calculator doesn't like real numbers, for sure. Or it doesn't like not real numbers, yeah. Okay, so pretty much anything you can think of, aside from those things. All right, so we're going to use this in kind of our language for domain. So domain, every single time I say domain, I want you to think X and I want you to think horizontal, okay? So domain is the set of all possible X values of a relation. You okay back there? Okay, and I want you to think, when you think domain, I want you to think left to right, horizontal. Okay, now what we're going to do is we're going to set up kind of like a mathematical sentence. And the sentence is kind of formatted so that we are all using the same format, right? Because if I'm using a format and then Tony's using a format and Olivia's using one and we all use different things, then there's no common language, right? So the common language, just like in English, we have all of our grammar rules and stuff like that so that we're all on the same page. No pun intended with English and books and things. I know. We also want to be on the same page as far as like the mathematical language that we use, just so that people can understand what we're saying, right? So when we set up domain, we are telling people what the set of all possible x values of our relation could be, and this is how we set it up. So we signify that we're doing domain with a capital D, not too bad. And then we're going to do a colon, which basically just says domain is. And then we open a set of curly brackets. So y'all are gonna, oh, how do you know that? Grade 10? Oh. Okay, so y'all are gonna have to practice your curly brackets. You gotta practice. Okay, so Claire is correct. So what we're going to do is this. We say x, because domain deals with x. And then we use this like curved E. That was actually really bad. We use this curved E. So it's kind of like a mix of a capital E and a lowercase e. But it's a curved E. And then we use the real number symbol. And what this part of the sentence says is x is from the set of real numbers. So it's a part of the set of real numbers. So we're going to write that below. Or sometimes we say that that little e represents is an element of. But we can just say is part.
Wait, what are we even writing?
We're writing a math sentence which will tell the reader the possible x values of a relation. Yep, so this means x is a part of the set of real numbers.
Oh my gosh.
Okay. All right, do we need a little break after this? Okay, stick with me for these next two definitions, and then we'll take a little break before we do some examples. Okay, next part of this, we're going to write a bar, and the bar just means such that. Okay, so, did she? That's good. That's her name. You're right. Okay, and then the second part of this will be different based on the different scenarios that you have. So I can't give you a perfect, this is what you have to do for this. It's just what x can be or what x cannot be, depending on what's more efficient for us to write. So you'll either tell the reader x can be this set, or like x is greater than 3, for instance, or you'll tell them x cannot be 2, or something like that. So either sometimes we write what x can be, or sometimes, if it's more efficient, we would write what x cannot be. Okay, and we have to kind of choose based on the scenario that we have which one is the better option. Carla? I think usually we defer to like what x can be, unless it's like one single value or like one or two values, and then we'll say what x cannot be. Okay, Carla?
I'm actually not desk. Can I take this? My dad's trying to like call me or something.
Yeah, just step out.
Tell them to say hey.
Alright.
Okay. Range is going to be pretty much the exact same thing except with y's, okay, and r for range, okay? So when we think range, I want you guys to think vertical, up and down. It's the set of all possible y values of our relation. And then we're going to set it up similarly, but guys, focus in for like 10 seconds here, and then we're going to take a little break, okay? The important thing is that we remember to switch this to obviously R for range, and then we're using all Y's. So it will look very similar. We're going to have curly bracket, Y is an element of real numbers, such that the curly bracket, you got to practice, man. And then we're going to write either what Y can be or what Y cannot be, depending on, again, what is more efficient. Usually it's what Y can be. Okay, and then you're going to close up your curly bracket. Okay?
Can I just do squiggles?
Yeah, do your best. All right, so we're going to take a quick break here. Zoom this. Okay, so this X is an element of real numbers part. I mostly use this if I have a graph that goes like a continuous graph. So you guys remember we talked about continuous and discontinuous yesterday? So continuous meaning like I have like parts of that graph I can trace all the way from one part to the next part without having to lift my pencil. Now if I just have a set of points, I don't think it's really necessary for me to like indicate a whole set of numbers. So what we would do if we just have a set of points is we'll still set up our little like domain and curly bracket thing here. And then usually what I would do is I would just say X equals, and I will list the X values lowest to highest, kind of like we do in that mapping diagram with no duplicates. Okay, so it will be X equals, and then I will take each of these X coordinates, lowest to highest, no duplicates. Okay, it's not necessary for me to include the whole set of real numbers and everything because I'm literally telling exactly what X is equal to here. Okay, so X equals these things. All right? And then we're going to do the same thing with Y.
Thank you.
Yep, have a good day. All right, so range, and then Y values, lowest to highest, no duplicates. So these guys are what I'm looking at here. -2, 3, 4, 5, 6. And close up your curly bracket. Okay, so this is the format that I will use for a set of points. Okay, and a table of values is nothing more than a set of points as well. So we're going to use the same format for this table of values here. We'll do domain, and then we're just going to go X equals 1, 2, 3, 4, and 5. And then same deal with the range over here. Y equals lowest to highest, no duplicates. 4, 7, 10, 12, 17. And we're done. Okay, so that's how we're going to approach a set of points. Now the definitions that I kind of showed you above, these are more like if we have a graph that has like all the little decimals in between those values that we want to include. For these ones, I know that X is definitively 1, 2, 3, 4, 5. That's all that X is equal to, actually. I don't want to include like 1.5 or 2.5 or any decimals in between those values. So I actually just want to explicitly say, these are the X's and those are the only X's. Ivana?
Do you want us to identify if it is a function or just a relation?
So we can just talk about this verbally, but unless I ask in the question, like, is it a function or a relation, then you can say. But is our first one a function? No, why not? Okay, we have -2 matching up with 2 different Y values. What about number 2? Is this a function? Yes, this is. So as soon as I look at the X's and I notice that there's no duplicates, I can say it's a function right away. Okay, so set of points, not too bad. Just list the X's, lowest to highest, and you're good to go. Okay, graphs. Now, remember, domain, you want to think X, and you want to think horizontal. Okay, range, we want to think Y, and we want to think vertical. Okay, so commit that to memory. Domain, X, horizontal. Range, y's, vertical. So we're going to start with domain for this one. And we're going to just open up with our x as an element of real numbers. Sometimes if x has no restrictions on it whatsoever, so if x is everything, we'll just close it with a curly bracket there. I can already see that there's boundaries on this function though, right? Or this relation, maybe I should say. So I'm going to say such that. And then here's what I want to do. I want to do the lower boundary to the upper. So, and then I'll close my curly bracket there. So, and then when I'm talking about lower to upper, I mean left to right for domain. So, what is the very furthest left that I can go on this? Claire? Negative 2. And what is the very furthest right that I can go? Positive 2. Now, I also, so you may be asking yourself, okay, well, why don't I just say what I did with the points up there and say x equals negative 2, negative 1, 0, 1, 2. Well, the points all between those values are actually included on this function as well, like all the little decimals in between negative 2 and negative 1, and between negative 1 and 0. Those little decimal values, those are all part of our set as well. So it's not single points this time, right? Ivana? Yes. Yep. So that's exactly what we're going to do. We're going to use inequalities. So I'm going to put my lower boundary and my upper boundary, left to right. I'm going to put x in the middle because I'm telling what x is. And then I'm going to use inequalities. So this is a two-sided inequality. It's saying that x is, we want to say x is 2 and lower. So I'm going to say x is less than or equal to 2. So if I read this way, I can see x is less than or equal to 2. And then I kind of want to read this part backwards. So I want to say x is greater than or equal to negative 2. So the big part is facing toward x, and the little part is facing toward negative 2 here. So x is greater than negative 2, but also less than 2. And it's also equal to those points because those are actually on the function, or relation, I should say, for this. So it's everything from here all the way to here. Okay? And then range, we want to think y and we want to think vertical. So we'll set up our y as an element of real numbers. Okay, again, I can already see that there's boundaries on the lower and upper parts of this function. So I'm going to say such that. And then if I have two boundaries on my function, I will put the lower as in going down to the upper as in going right or going up. And then I will write what boundaries y has. Okay, so what is my lowest part of this function? Claire? Good? Okay. Highest part of this function, Alex? Positive 2, good. And everything in between that, right? So every single point in between that, all of these little guys all the way up, I want to include those. So it's actually going to look pretty similar to this, except instead of an x, we'll have a y. So it goes negative 2 to positive 2, and then I want to say it's greater than or equal to negative 2, but less than or equal to 2. Okay, now not everything is going to have two boundaries on both sides. Sometimes there might be a boundary on one side, in which case you're just saying something like x is less than 2, or x is greater than or equal to 3, something like that. Okay, so this is actually a good example of that. Any questions on this one before we continue? Okay, this does require a little bit of practice, so don't get freaked out if you're a little bit confused. Okay, so we'll notice firstly that there's little arrows on the end of this guy. So we're going to imagine this going up and also expanding forever, right? So to infinity and beyond. So let's think horizontal to start. We're going to start up our domain expression here. So x is an element of real numbers such that, okay, left boundary. Is this ever going to stop going toward the left?
No.
It actually keeps getting wider forever, right? So does it stop going toward the right ever? So is there anything that x can't be here? X can be everything, right? Oh, you're thinking vertical though, you're thinking range, right? So let's think horizontal. This is gonna get wider forever. So x is actually all real numbers. Okay, it's everything. Just goes forever, right? Okay, y, Karen.
What is this? Wait, we don't write the bar though?
So there's no restrictions, right? So x is just everything. We don't have to say,
The bar means.
the bar usually means like such that, and then we say like x is between -2 and 2, right? But this one, x doesn't have any boundaries on it.
Why can't we just use words instead of letters?
Well, like I said before, we want to have just like a common language, right? That we're all using.
English.
So,
We all
yeah,
use English.
true.
Not all of us use English.
Okay, so range, we're gonna think vertical. We're almost done, guys. Just hang in there with me for the last few minutes here. Lower boundary for y. So let's start with range. Y is an element of real numbers. Is there a bottom of this function?
-3.
Not -3. +3. Is there an upper part of this function? No, there is not. So this is actually kind of more like a one-sided inequality, right? We just have y. So what I want to say is a sentence that says 3 and above. Y is 3 and above. How do I say that mathematically? Ivana?
Greatest to, no. Greater than or equal to.
Yeah, 3. That's right. Okay, also equal to 3 because 3 is actually a point on the function, right? So it's equal to 3 and then above. Good. So 3 and up from there. So far, so good? Okay, we're going to try a couple more quickly here. We're going to go a bit faster so that we can do some individual practice today before we leave. Someone help me with domain for this one. Do we have a very left side boundary here? Ivana?
Yeah, it's x and greater than or equal to 0.
Great. So it's 0 and forward when we're talking about domain. So x must be greater than or equal to 0. Okay. Now with y, again, we kind of have to imagine that this function is growing forever. It's growing upward and it's growing toward the right.
How do you know which way to like make the... Never mind.
I have to decide if it's 0 and above or 0 and below, right? So the bigger one, if I want to say greater than, the bigger part should be facing toward the x, right? X is greater than 0. Okay? All right. Does this have a bottom boundary on it?
Yeah.
Sam?
0.
No? Yes? No?
Yes, there's a boundary.
What is it, Sam?
0.
0, yeah, it is. So this is the very lowest point of my function. Does it have an upper boundary? Is this ever going to stop growing toward the top? No. So actually our expression is pretty much the same except for with y for this one. Any questions on that one? Okay, so remember y, vertical, that's range, domain, horizontal, that's x. Claire, can you take out your headphone, please? Yeah, not too stealth there if you're like going like this in the back. Thank you. Okay, last one. Okay, so this function, what's important to know is that this function has two pieces to it, so it's a discontinuous function, but both of these are part of the same function. The other thing that we need to know here is that, see how this function's like curving around certain areas here? This function has kind of like these imaginary lines that it naturally avoids, okay? And they're called asymptotes. So,
They're called what?
I know, it's hilarious, okay? Asymptotes, okay? So that's what it is. These are imaginary lines that our graph kind of naturally avoids. Okay, it's right here. Okay, and these are caused by certain things that happen in our function. For instance, I can't divide by 0. So if I happen to have a fraction part of my function where there's a part that could potentially be equal to 0 in the denominator, that's what happens graphically. So I don't want to, that our graph naturally avoids. Our graph will actually create these kind of imaginary lines that it curves around because of what is happening algebraically. We'll talk a little bit more about that later in the course. Okay, so really quickly here, what is the equation of any vertical line? What's the equation of any vertical line?
Wait, is that the only type of like asymptote that there is? Or
Like-
does it look like, or is there more asymptotes that look in a different way? Is that,
They'll either be vertical or they'll be horizontal.
okay, so can you like automatically tell if it's an asymptote or not? Like it'll always look like that?
Yeah, it'll kind of like curve around. Yeah.
Okay.
Okay, so what is the equation of any vertical line? X equals the number that it cuts through, okay? So any vertical line, we want to think x equals, and what about a horizontal line? Good. So horizontal line, we want to think y equals. So can somebody tell me what the equation of this vertical line for this guy is right here? Ivana? Well, the equation of the line is just x equals 0, right? But for domain, we're going to put a slash through it to say x cannot equal 0. And then how about this horizontal line? Y equals 0. Okay, good. So when I write domain and range here, you'll notice that there actually isn't really boundaries on this function. So I'll start with x as an element of real numbers. And then we're going to do the such that. But you'll notice that this function is actually going forever toward the left and also forever toward the right. There's just one value that this function hops over horizontally.
Are we gonna have a review day for this?
2.
This is a lot.
I know, it's a bit of a longer unit. Okay, there's one value that my graph is avoiding, one x value. Okay, so this is a case where because x is literally everything except for one value, we just say what x can't be in this case rather than what x is. So we're going to say x cannot be 0. Okay, it just hops over that part. Okay, and then similarly, when we think vertically here, this guy actually goes down forever and also up forever. But it just hops over one y value right in the center there, which is the y value 0, right? It goes all the way up, and then you actually have to hop over to continue that. So here we would also say y cannot be 0, just because of the placement of that asymptote. Okay? Asymptotes are not always on the x and y axes. They might move. So you might just have to pencil them in and kind of see. But every scenario is different. So we have to just see what we approach and then see if we can kind of figure it out. Okay? So I'm going to stop this now.